So this week in lab we'll be looking at how solvent polarity can affect the rate of an SN1 reaction, and specifically we'll be looking at the solvolysis of two different alkyl halides. A solvolysis reaction generally is a reaction where the solvent acts as the nucleophile. In the reaction we're going to be looking at, water is our nucleophile, and we'll be using two different alkyl halides as our substrates, T-butyl chloride and 1-chloro-1-phenylethane. Recall that SN1 reactions are, like solvolysis, are first-order reactions. That means the rate is equal to the rate constant times the concentration of the substrate. Recall that the rate of the reaction is determined by the rate-limiting step, which in this case is how fast the carbocation can form. So we're going to form the carbocation here. And remember, this is a tertiary carbocation, so it is one of the easier carbocations to form. The other substrate that you're going to be using is 1-chloro-1-phenylethane. And this carbocation, even though it is a secondary carbocation, is also stabilized by resonance due to the presence of the aromatic or benzene ring. So we can show resonance forms for this. There's the first resonance structure. There's the next resonance structure. And there's the last resonance structure. Recall that the actual structure is a hybrid of all of these resonance forms, and of these, the resonance form I'm circling is the one that is the most contributing resonance forms. And the reason for that is these other resonance forms, notice how the aromatic ring isn't complete, so these are definitely higher in potential energy than the resonance form I've shown here. So we have a tertiary carbocation that we're forming, and we also have a secondary benzylic carbocation that we're going to be forming in these reactions. So let's look at the overall mechanism for the reaction. First, as we just pointed out, we're going to form the carbocation, and then water is going to come in as the nucleophile and form a bond to that carbocation. That's going to give us, we're getting closer to our product now, and then another molecule of water, because remember it's the solvent, so there's lots of it around, can come in and remove that proton. So that's going to give us our alcohol, and it's also going to give us the hydronium ion, which is going to be equal to the concentration of HCl. And that's really important in this reaction because this is the concentration that we're going to be monitoring in order to figure out what the rate of the reaction is. So here's the reaction coordinate diagram for a first order reaction like an SN1 reaction. And this is forming the carbocation intermediate here. And recall the rate-limiting step of the SN1 reaction, as we said, is the first step of the reaction, and there's the transition state I've just highlighted that. Here, delta G double dagger is the same thing as energy of activation. That's just another way of saying it. And recall that anything that stabilizes the carbocation intermediate will also stabilize the transition state. And if you lower the transition state energy, that means you're going to lower the energy of activation, and that is going to increase the rate of the reaction. So what are some of the things that stabilize carbocation intermediates? Well, polar solvents can definitely stabilize the carbocation, because recall you've got this polarization, delta positive and delta negative, and so that delta negative can stabilize the carbocation there. And recall that polar protic solvents, the ones that can undergo hydrogen bonding, can also stabilize anions, which means that in this case, that they'll also be able to stabilize the leaving group, which is chlorine, which also helps increase the rate of the reaction. Solvent polarity, it can be measured by something called a dielectric constant, and basically the higher the dielectric constant, the more polar the solvent is. Here's a table of dielectric constants. I've also uploaded this table to Canvas. And solvents, as I said, that are more polar, stabilize the carbocation. And so you can see here that this group of solvents, are the solvents that we called polar protic solvents because they can undergo hydrogen bonding. And you can see that all of them are very, very polar. Especially if you compare them to, remember, these are called polar aprotic solvents because they cannot undergo hydrogen bonding, but they are somewhat polar with solvents like acetone, and we're called DMSO. Those are very, very polar compared to the other solvents. And finally, just for comparison, I put in the dielectric constants of some of the nonpolar solvents. The solvents that we're going to be using in this experiment are water, ethanol, and acetone. So here's a reaction coordinate diagram that gives you a sense of how the reaction is going to change in it with nonpolar solvent versus a polar solvent. You can see here that the delta G delta G double dagger, or energy of activation in the polar solvent, is much lower than the delta G, or energy of activation, in the nonpolar solvent. And here you can also see that the nucleophile is stabilized a little bit, but that is definitely offset by the overall lowering of the delta G double dagger. Okay, so here's our reaction mechanism again, just to remind us what's going on. And here we have the rate equation for the reaction. The negative sign in front of the equation indicates that this is the rate for the disappearance of the alkyl halide as it's being consumed in the reaction. And the rate of disappearance or consumption of the alkyl halide in the reaction is equal to the rate of appearance of HCl. So how fast the alkyl halide is consumed is equal to but opposite in sign, the rate of how fast the HCl is formed. And that's convenient because we have a hard time measuring the concentration of the alkyl halide, but we can measure the concentration of the HCl. Okay, so rates themselves can be hard to measure because you're measuring something that is changing over time. However, if we integrate the rate law by first separating all the variables and then integrating, we get the integrated rate law for the reaction. Yay! Why is this a yay? Because now we can plot a line. Yay! And you know that we all love anything where we can make a straight line where y is equal to mx plus b. Yes. And the slope of this line, as it's pointed out over here, is equal to k. So awesome. Because the rate of the reaction is proportional to the rate constant k. And that just means bigger rate constant, faster rate. So I wanted to point out that what this variable here is, this is the concentration of the alkyl halide that's the infinity symbol, and that means at the end of the reaction. And then, oops, I left out a bracket. And then this is the concentration of the alkyl halide at any time t. And as I said, it is hard to measure the concentration of the alkyl halide. So what are we going to do? Well, remember that HCl is a product of this reaction. And for every 1 mole of alkyl halide that is consumed or reacted, 1 mole of HCl is produced. So the concentration of the alkyl halide at any time t is equal to the initial concentration of the alkyl halide, and we subtract from that the concentration of HCl at any time t. And so what we're going to do is we're going to titrate that HCl as it's formed. We'll use a burette, so flashback to Chem 112, and we will titrate the HCl with sodium hydroxide. Okay, so to measure the rate constant, what you're going to do is you're going to have an Erlenmeyer flask, and in the Erlenmeyer flask, you're going to have 50 milliliters of one of these solvent mixtures. So for example, in T-butyl chloride, one of the solvent mixtures will be 40% ethanol and 60% water by volume. Okay, and so then you're going to add a couple of drops of bromethymol blue indicator to the flask, and then you're going to add from your burette about 2 milliliters of sodium hydroxide. Then you'll add the alkyl halide and you'll start your stopwatch. As you're timing it, you'll notice that the color changes from blue to green as the alkyl halide is being consumed and HCl is being produced, which neutralizes the sodium hydroxide. Eventually the color will change to yellow as all of the sodium hydroxide is neutralized and you start to have an excess of acid present. Then you'll add some more sodium hydroxide and the color will change back to blue because now you have an excess of sodium hydroxide again. So then you will continue to wait and the color change will happen again, and that will be your next time point. Okay, so after you've measured 4 time points, okay, so you'll have your 0 time point and then 4 additional color changes. You're going to allow the reaction to stand for an hour, and that's basically time is equal to infinity. So, and then what you'll do is you'll then titrate. You'll titrate the reaction until you get to the end point. And then you'll take all your data, and I have made an Excel template for you, and that will give you a nice line where K is going to be the slope. So here is the sample data that's in your lab handout, and one of the things I want you to do is I'm going to want you to plot this data in the Excel spreadsheet. So here's the table in the Excel spreadsheet. And this is where you're going to fill in the time in minutes, the time in seconds, and the burette readings from this table. And what will happen when you do that is, voila, it will figure out everything for you. And just as a reminder, what's in this column is what is equivalent to the y variable. Now you might be asking yourself, how is this the y variable? Well, that's because v infinity divided by v infinity minus vt, taking the natural log of it, is equivalent to what we saw was the y variable in the integrated rate equation. If you'd like to know exactly how that algebraic manipulation happened, you can read the endnotes of the lab handout. But the cool thing is not only does this Excel template do all of these calculations for you, it also gives you a nice graph. And as you can see right here, here is your formula, and so right there is your slope. So K is equal to 1.097 times 10 to the minus 3 seconds to the minus 1. That's the unit for the rate. Now, of course, sample data is a terrible title, so you want to double click on that and replace it with a more descriptive title like T-butyl chloride and 40% ethanol. Okay, just to summarize what you're going to be doing, you're going to be assigned, your lab group will be assigned either T-butyl chloride or 1-chloro-1-phenylethane. Yes, you will be doing this in teams. Once you get your data, you will plot that data with the Excel template. Then you will upload that spreadsheet to Canvas, and one of the things we're going to do is we're going to pool all the data as well as compare it to previous classes' data. So that's about it. Dudley wants you to remind you to be very focused during lab because you need to read the burette very accurately. And Rudy wants to remind you to not stress out too much and remember to take naps.